Assalamu alaikum everyone. I hope you are doing well. So this is my PSM2 final presentation on my research project, which is comparative study on LSTM and GRU model performance in sign language translation. I am Maria TASKIN AUMANEE. My metric number is A20EC3021. So without any further delay, let's move on to the presentation content. Firstly, I will be introducing you with the prospect of my research and its problem statement and objective. Then we will go through the scope of research and the literature review regarding it. And finally, the proposed solution from the literature review and the methodology, experimental design and code snippets. Finally, there will be result analysis and conclusion. So, introduction to ASL language, which is American Sign Language. So, in this world of several possibilities, researchers have benefited a lot from different modes of communication by fixing the gap between AI and computer vision. So, due to recent friendly use of gadgets in the present world, communication has become very diverse. And among all the notable languages, sign language translation is one of them. It reduces the interaction gap between the people with deaf and mute impaired. So, according to the World Federation of Deaf, there is approximately 70 million deaf people worldwide who can use sign language as their first language. And accurate sign language can actually mitigate the communication gap. So, why not make something good out of it? So, let's move to the problem statement of the research. Firstly, the deaf and mute community has communication difficulties due to lack of accurate and real-time sign language translation. Secondly, there is a gap in understanding the effectiveness of AI techniques in sign language translation, and this is research aims to provide an insight into the accuracy and scalability. And thirdly, existing sign language translation systems do not provide a thorough comparison between the most popular neural networks. So let's move on to how our objective aligns with it. The objective of my research is to study the existing literature on LSTM and GRU models in context to sign language translation. Secondly, to design and implement experiments for comparing the performance between them, and finally to analyze the experimental results and to identify which model is better for sign language translation in terms of standard model metrics. So my scope of research actually centers on the comparison of LSTM and GRU, and it uniquely evaluates the model performance, in which also includes the metrics like bilingual evaluation, accuracy, and precision. Thirdly, the dataset ASLGPC12 corpus, which is English ASL Gloss Parallel Corpus 2012, is been taken. It has a credibility rate of 10.0 and has a total of 87,000 data in the dataset. So, in the extensive literature review that I've already done in the paper, this summarizes. So, the literature review highlights the significant progress in using neural networks in SLT. And studies by researchers like Sujay and Pathak, they can effectively they can effectively launch a model which can recognize and translate ASL glosses to English, and these models can achieve high accuracy for capturing the timing and movement of the gestures. And some model also has accuracy rate of 99%. And GRU model also show the strong performance in sign language translation. For example, like research by Amin Hefni and Mohammed, they demonstrate that GRU models, especially when combined with the attention mechanisms in their model architecture, they perform very well in recognizing the signs. So they also use the same corpus as mine, which is ASLGPC12, and they also compared studies to show that GRU models can sometimes outperform LSTM models in terms of accuracy and training speed. So My research workflow for the whole thesis was they're divided into four phases. First phase for the literature review and problem formulation, where I did a preliminary study and review deep into the deep learning work, and then identify the used methods and their data sets. And then I compared the existing works of sign language translation and their efficiency. And finally, I chose two best models to compare. In the phase two, in the data collection and pre-processing, I have chosen the dataset ASLGPC12 corpus, and then did the pre-processing as needed. I'll be discussing about it later, and then I'll prepare the model. I prepared the model for implementation. And for phase three in the algorithm model, I set up the experiment needed for running the simulation. And then I chose the dataset and the model, which is the LSTM and GRU. I fit the data into the model so that there is no null values or no null subsets remaining. And then I hyper tuned the parameters. Um, Hyper parameter, and then I collected the result data, and lastly in the last phase I evaluated and the result and analyzed between LSTM and GRU and compared the performance, and finally I discussed the achievement and reported the documentation, and finally led to the completion of my final year project. So let's see what are the performance metrics um, for my models, which is BLEU4 score, which is bilingual evaluation understanding. So BLEU score rates how well each model works by checking how similar the created text is to a reference version. So especially it is helpful for checking the quality of machine generated versions against the originally written words by people. So it helps figure out how precise and correct translations are by looking at how many n-grams are there, they match up with other readings. So the second is the ROUGE score, which is Recall Oriented Understudy for Gesting Evaluation. So the ROG score is a measure of how to evaluate the quality of a summary by comparing it with the reference summary. So it checks how many words and phrases from the reference summary appear on the generated summary, and this score helps in determining how similar the two summaries are. It indicates the accuracy and relevance of the generated summary. So, in simple terms, it actually measures how much the generated summary matches with the reference summary. So, the methodology of the research flow is at first I load the dataset ASLGPC12. I check the null values. If there are any null values, I dropped null values. And if there are no null values after the loop, I continued with the data normalization, which takes normalization, noise reduction, and handling special characters. Then went to the tokenization, which opened another new column in my data set, and then I padded my data to fit all the data into the same padding, and then split my data into train and test, which is 80% and 20% ratio, and that's the end of my pre-processing. Let's move on um, to the flow where I introduce you to the data set. So this is the actual data set, which has only two columns, two features, which is gloss and text. Gloss is what machine is detecting, and text is what it is supposed to be translated. And later, when I pre-processed the data and tokenized, it turned into three columns where it tokenized the gloss so that each word is identified during the simulation. So let's go into a detailed description of the experimental design. Firstly, the model architecture of GRU. As we can see that in the figure, when we give the gloss notation, it does the pre-processing and put it through four layers, and then go to the encoder and go to two more layer, and then after all the neural machine translation is done, it is finally translated into natural language text. And at the right hand side, the figure is actually the parameters of the layers. So the input layer takes in the sequence of 36, and none represents that the batch size can be anything. And embedding layer, it converts the input sentences to 128 dimensional dense vectors. And the first GRU layer processes sequence to capture dependencies over 36 time steps. And GRU second layer defines refines the first output, the sequence data, and the time distributed dense layer transforms each step's a 120 dimensional output into 3646 dimensional vector, which corresponds to the vocabulary size for generating the output. So, similarly, in the LSTM model architecture, we see there one less layer than the GRU model. So, in the input layer, it will accept a sequence of 42 features. In the embedding layer, it will convert each feature into 120 dimensional vector. And the LSTM vector will process the sequence into 120 dimensional vectors to capture the dependencies. And finally, the dense layer will transform the LSTM output into 5909 dimensional predictions for each time step. Okay, let's move on to the code snippets. So this is the GRU model code snippet, and first window is for the libraries that are required to simulate the data set. So as you can see, I've imported the pandas and NumPy and TensorFlow, Keras, and for all these libraries, each is defined for each function. So NLTK is also used for BLEU score, and RUGE underscore score is one of the main libraries to calculate the ROUGE score. So finally, when we load and process the data set, it drops the rows with the missing class token. So it when we select the data of 3000 data from 80,000 plus data, it definitely has a million null values. So amongst that, it will drop the rows with a missing class token, missing or null values. So it will tokenize the gloss token and then convert the gloss token to the sequence by the tokenizer dot text to sequence function. And then it will pack the sequence so that each token or each data is not each data is perfectly padded, and then it will prepare the features x and y, um, and then reshape y so that it does not exceed the x value, and it will convert y train and y test into categorical vocabulary size. And then it will split the data into training and testing sets, so at a ratio of 80% and 20%. Finally, to define the GRU model, it will have an embedding dimension of 128, and it will call the sequential model and the time distributed, as we previously explained, the parameters, dense layer and GRU layer, embedding layer, and they'll compile the layer with model.compile function, and it will use the Adam optimizer and use a categorical cross entropy for the accuracy matrix. And finally, it will train it and will extract the training accuracy and validation accuracy. And after that, once the accuracy validation accuracy is reached, so it will calculate the ROUGE and BLEU4 score. So BLEU4 score is directly calculated through its library, but ROUGE score needs precision and also um, the brevity penalty. So these are the equations and steps to find these two quantities. Finally, once we find the average ROUGE and BLEU4 score, it will append those in a CSV file. And finally, the training accuracy, validation accuracy, and test accuracy will also be found. So similarly, for LSTM model code snippet, it will import the libraries needed to simulate, and then according to the libraries, it will load the data set, and then it will remove with empty class token. The all the steps are similar to GRU except the model architecture. So it will again split the data and split it into y and x variables, and then it will define the model. The model is a sequential model at embedding LSTM and dense layer, and then use categorical cross entropy and Adam optimizer also. Finally, it will convert predictions and ground truths back to the text. So for this, an extra step is to calculate the n-gram precision. So BLEU score will be calculated through log precisions, and all the equations are inputted manually. So finally, BLEU1, BLEU3, and ROUGE score is calculated, and average has been found out, and the train accuracy, validation accuracy, and test accuracy is calculated. So let's move on to the evaluation and the result that I have found in my study. So this is the validation accuracy and LSTM and GRU. As we can see in the 50 epoch, um, um, the x-axis is drawn as the 50 epoch, and for y-axis I have kept the validation accuracy. So the horizontal axis will contain 50 epoch. So after a 50 epoch of input, GRU model produces almost one of the validation data, and LSTM model is slightly higher than the value of 1. And so comparing the two components, it will be seen that the GRU model has a higher validation accuracy than the LSTM model. And in the validation loss between LSTM and GRU, the graph is plotted as x-axis to the 50 epoch and y-axis to the validation loss. So find at the 50 epoch, the GRU model has a smaller validation loss as compared to LSTM. Therefore, the model will give a better accuracy and converge very easily, and the validation loss of GRU model is lower than the LSTM model at each step. Now let's compare the accuracy of the test data, validation data, and compare training data. As you can see that the GRU model outperforms the LSTM model here also. In training data, LSTM has an accuracy of 89%, but GRU has 99%. So it will be more efficient in training data, GRU. And validation data has a percentage of 94 for GRU and 84 for LSTM, which also indicates that GRU model has a better generalization of unseen data. And test data, in which GRU also have a 94%, and 10% less than GRU is LSTM, which is 84%. And it will show how robust and superior is GRU model in terms of performance. So these are the score, performance comparison in terms of score. So I'll delve more into it in the next few slides. These are the primary graphs for it. So as you can see from the graph, we have tabulated the data, and then here we can see that GRU model outperforms at every score than in every score than LSTM. So in the BLE EU4 score, GRU is 41% and LSTM is 17%, which means that LSTM is slightly less in producing more contextually accurate and coherent translations. So higher BLEU4 score means that its effectiveness is more in capturing and generating longer sequence of words aligned to the reference text. So in ROUGE1, which works for the unigrams, GRU scores are 73% and LSTM is 52%. So this indicates that GRU is better at capturing individual relevant words from the reference summary. ROUGE2, which works for bigrams, in which GRU scores 74% and LSTM scores 24. With a huge gap of score, it proves that GRU has a better ability to capture pairs of consecutive words. And it reflects a better understanding of short phrases like consecutive phrases. And ROUGEL is the longest common subsequence. Here, GRU scores 73% comparing to LSTM, which is 51%, which proves that GRU is more effective in capturing longer sequence of words, indicating better overall summary structure and coherence. So finally, after the evaluation, the analysis actually demonstrate that how GRU outperforms LSTM in both BLEU4 score and ROUGE score. Higher the blue score of GRU, it indicates its ability to generate contextually accurate and coherent translation. And also in ROUGE score, the GRU reflect a better performance than LSTM, which means that it has effectiveness in producing high quality translation and summary. It makes more suitable choice for sign language translation tasks. Thank you everyone for patiently listening to my presentation. That's it.